Hello and welcome to the Open Systems Media webcast titled VME Bus in Military Systems. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. Our panel speakers today are Nigel Forrester, Director of Product Strategy, Concurrent Technologies, Rob Persons, Senior Pre-Sales Architect with Smart Embedded Computing, and Ken Grope, Director of Embedded Computing Architectures at Elma Electronic. Today's webcast is sponsored by Concurrent Technologies, Elma Electronic, Smart Embedded Computing, and hosted by Military Embedded Systems Online and Open Systems Media. Now, before we begin, I got some housekeeping items to go over. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. The webcast will consume about 45 minutes, leaving the remaining time for the question and answer session. Now let's take a look at that viewing console. It has some important features I want to run through. The console consists of a set of windows that you can close, open, move, resize, and maximize to your personal preference. On entry, you see a picture of our presenter in the presenter window, biography in the speaker bio window, presentation slides in the slides window, and a Q&A window that will enable you to ask questions during the event. There are a set of 7 icons across the bottom of your screen. Clicking the icon on the far left resets your viewing area to the default configuration. The rest of the icons will open or close their corresponding window. Just hover your mouse over each icon to show which window it controls. The handout icon third from the right opens the handout window, which has presenter slides in PDF format to follow along with or download for future reference. It also has a recent article in Military Embedded Systems magazine written by one of our speakers, Rob Parsons, titled VME, Not Time to Die. So take a look at that when you have time. And the Q&A window enables you to participate in today's event. You simply type a question into the Ask a Question text box and hit Submit. If you have a question intended for a specific speaker, please note so at the beginning of your question. Otherwise, I'll hand out all the questions equally to all of our speakers. If you have a question pertaining to the webcast operation itself, one of our technicians will get back to you during the webcast. We encourage you to ask your questions throughout the event while the question is still fresh in your mind. We'll then address as many as we can during the closing Q&A session. Please note, as much as we'd like to, we may not get to all those questions today. In that case, someone might get back to you after the webcast for more information. The webcast will be archived online at the URL shown on your screen and be available within 24 to 48 hours. Once up, it will be available for 1 year. Now I'm pleased to turn it over to our first speaker. Rob, take it away.
Thanks, John. Get to my first slide here. Okay. Yes, as John mentioned, I'm Rob Persons. I'm with Smart Embedded Computing, and I'm going to start off this webinar by giving a kind of a brief background to VME itself, what the standard's about. Probably many that are joining the call probably already have some experience with it, but I just want to use it kind of as a level set. Really go over some of the real strengths of the standard and why it's been around for such a long time and why it's still going strong. Maybe not as strong as at 20 years ago, but it's still going on quite strong. So let's get started and begin with the discussion about the standard itself. VME is really a group of technologies that are managed under an organization called VITA. VITA stands for VME Industrial Trade Association. And it really was an attempt back 40 years ago to try to standardize on a set of technologies for embedded computing, which included processors, memory, and I/O. And from that point, it is really diversified into a wide range of technologies, even into brand new bus architectures that are no longer based on the original VME backplane. This all started back in 1981. That's the real birth. That was the first early edition of the preliminary standard. Let's put it that way. And where various companies got together to actually create a standard. Believe it or not, originally around the 68,000 bus. That used to be a Motorola semiconductor-based processor, and then technologies were built upon that. So, if you look at the original VME bus backplane, it really looks like an early 68,000 bus. Later, when the standard actually was ratified in 1985, it showed in this industry that there was a way for different companies to actually create products around a common set of goals and customers be able to buy this product and interchange them. And that was really the starting point of an expansion into a wide range of technologies that various customers could use to actually build up a lot of the modern day military systems that are out there today. But that's not the only point in time where it was actually, it's just not a single standard. It's actually an evolution of a set of enhancements that happened over time to add additional capabilities to the backplane itself. Things like being able to increase the speed with new uses of the address and data lines in the backplane bus to really create a high-speed interconnect for a variety of I/O cards and processor cards in these systems. So the VME Bus technology expanded over time, enhanced over time, but also maintained that backward compatibility with the previous generation of products. So every new standard didn't just create a new set of products where the old ones were thrown away. They were able to be used over time and be able to be able to communicate between the new cards and the old cards. But not just the bus, we also started to see new changes in way that I/O were added primarily to the boards themselves. Instead of it being a separate card inside the backplane, we now saw standards which would increase the functionality on these I/O boards, compressing the amount of capability per slot in the VME Bus system. And even further beyond that, we started to see new enhancements to the underlying bus itself when new things like serial buses began to become important and the need for higher and higher performances between the I/O devices and cards were needed. Then new versions of these buses were actually created. Theoretically, you could also have hybrids of these. So the old VME Bus and the VPX bus could be in the same enclosure. But it's to address these higher and higher performance needs of applications that are taking advantage of any of these VITA standards. So what we saw in parallel as these technologies improved, we saw higher and higher levels of integration, being increased. So the amount you could get done in a 19-inch rack enhanced as the standards developed. And also we saw greater capabilities per slot. So we saw compression of how much you can get done in a single slot. So this graphic really shows a good example of how all these expansions in this technology over these years have improved from a 40 megabits per second original bus all the way to the enhancements done in the 90s for the 2ESST to get 320 megabits per second of transfer speed over the native bus while maintaining backwards compatibility. But then we see these expansions into newer technologies like VPX, where we see well beyond the performance that we saw in the original VME. But all these different technologies are still coexistent. I mean, they may not all operate in the same chassis, but they're all under the umbrella of VITA. And many of the companies here that are talking today here have all been involved in some way to enhance those standards. So why is VME still strong after 40 years? I think it had to do a lot with the fact that it was really the first major successful open standard developed. If you think of the time frame when this happened in the 80s, when PCs were just starting to come into existence, and the need for non-proprietary computing was really becoming more important, VME showed up at that same time. So prior to this, many military computer systems are all proprietary, custom built. And there was a need to move away from that. And VME was the real first standard to really address that. This is also interesting because this is the first time vendors and customers work together on a standard. I mean, in the early days, it was really more vendors, but as the VITA organization progressed over time with these new standards, we saw this influx of customers, actual people using these devices, impacting how those capabilities and how the standards kind of matured. The standard originally standardized on, and it still does, on a specific Euro car design. So the shape and size was very important in that early standard, and it's progressed all the way through. And I think that's been very, very good on keeping this standard around. Another big part was the fact that it had a good way to do multiprocessor support when multiprocessor really wasn't even in the cards in these early systems. So the backplane design really allowed for a great way to distribute processing and to easily add new capabilities over time. So a basic system's been designed, you need to be able to have additional processing capability. You could add a card in there and integrate that into the existing system. And a lot of other technologies really don't allow you to do that very easily. And the fact that the standard wasn't static and it matured and it continually added new capabilities over time, I think really has given it this kind of life. And the biggest thing I think is backwards compatibility. You're not throwing away a design just because you need some new things or you need to add some more capabilities. I'm going to migrate on now to a portion of how we as Smart work with our customers in migrating some of their legacy systems and some of the factors that are involved with how you decide to go and, which kind of processor do you want to move into if you have issues with the old one or if you need to have new functionality, and some of those questions and answers that you have to go through when you're thinking about migrating. Smart is really an amalgam of a bunch of different historical VME Bus companies. The major ones were Motorola Computer Group. We actually, our old CTO was one of the original persons involved with the standard, Shlomo Patel. He was actually one of the very, very early engineers working on the original standard. He's since retired, but he was there. He was with us for a very long period of time. We combined and acquired Force Computing, which was also another major player within the VME Bus space, and then eventually actually combined with Artisan, which originally was founded as Huracon back in the early 70s, to where we are now all really those legacy companies are all part of Smart Embedded Computing. The processors that we focus on are NXP-based processors. This is really kind of historical because the original Motorola Computer Group really spun out of the Motorola Semiconductor Group. And we're using those same processors today. NXP has the core architecture, power architectures, and that's what we focus on. We have a variety of older boards still in production along with some newer ones. And that's kind of the decision process here and kind of what I'm using as a foundational piece to the discussion about how you migrate. We end of life the product that's not on this list right now, the NVMe 5100, and we have many customers that have used that and are trying to figure out what do they do next. And some of these that, we deal with a lot of legacy customers, so they've been building these things for a long time, and some of the reasons why they haven't migrated, some of these programs haven't migrated are, they have a specific need for a backplane pinout. You wouldn't believe the number of times that a backplane impacts what you can do with a program. A big part of this is software, and it's software that was built many years ago, dependencies on old end-of-life operating systems. We have situations where there are applications out there where the original engineers have died, have retired, but they still need to maintain this thing and keep these systems alive. And there's also a lot of legacy IO that some vendors actually, some of the people actually integrating these systems produce and make. And Ken will talk about, he's one of my all-time customers that actually produce those kind of products. So why aren't they moving to newer technologies? Typically, budgets don't allow for it. you don't have any money in a military budget to be able to migrate stuff that's radar systems that have been around for a long time. Custom I/O can cause some problems. They have the need to talk to some legacy I/O, and migrating away from moving to newer technologies makes it very difficult to do that sometimes. And believe it or not, the system still serves a purpose and it works. So we have a lot of interest in staying here because they've got a system that works and they don't want to move it. And now we've also seen a situation where there are some impacts starting to show up. One of them, as an example, was the end of life of the TSI 148, which was a very popular VME Bus bridge that went into life in 2015. A lot of vendors actually replaced that with an FPGA. We decided just to buy a bunch of parts and maintain our boards as best we can with the supply, and we're actually doing pretty well with that. So we just decided just to buy the bridge, stockpile it, and continue to produce products based on it. So what drives the need to migrate? So there are times when you need to move away from your current processor, like the 5100 going into life, and what do you have to think about as you do those transitions? Primarily, the things that really cause a lot of problems are major components like the processors and the host bridge. Our 5100 went into life because we had a custom ASIC that we could no longer found. So it's driving people to have to think about what they're going to do next. Maybe they have a need for additional capabilities, new features, or spare capacity, tracking more targets. So they may want to move along to another processor board because of those kind of situations. The need to consolidate applications. They want to reduce the footprint of how many processor boards are actually operating on a particular task. Maybe they want to migrate into, say, a dual core design for these applications. And there's also the desire to move into newer operating systems, like later versions of a particular real-time operating system, or try to migrate into Linux. So some of the key decisions that we run across when we're talking with people about this are, what's the best reason to migrate to a new board? Maximum product life, maximum performance, and newer features available. But that's not always the point at which you actually would want to move to a new board. Sometimes you need to stick to an older board, and that's typically around older operating systems. There's no budget to migrate to a new operating system. There's changes between backplane pinouts. Like our newer boards have a different pinout than the old ones. Maybe the old ones, you have to stick to the older style boards because they have the right pinout for the backplane. In a lot of cases, newer products are multi-core. Applications are not well suited many times, the legacy ones, to move to an SMP or an asymmetric multiprocessing type of design. So why move? And then again, for legacy I/O concerns. And I went a little long, so I'm going to pass it back to John, and he can continue the webinar.
Rob, you did just fine. Nice presentation. And just a note to the audience, I see some questions already have come in. Keep them coming in as you think of them, and we will get to them during the closing Q&A session. Now to our next speaker, Nigel Forrester. Take it away.
Thank you very much, John and Rob, for a great introduction there. So there's my email address on the screen if you need to contact me after this webinar. And I've also put a link here to our VME products. So very quickly, I should say that Concurrent Technologies focuses on Intel-based processor boards. That's our major in life. And we currently have three new generation or current generation VME products on the market. We have a couple of older generation processor boards that are partway through their end of life cycle. But we've tried to segment our products so that we have, a very cost-effective Atom-based product. We have a generation of products in the middle on the slide here that are more flexible, more expandable. There's a way of connecting these to a second board to allow additional PMC or XMC I/O for expansion. And then at the bottom left, we have a board which is our highest performance VME product, but it's also the best for security. And a large part of my presentation today is going to be on what we're doing and what we've done to make our VME products relevant for modern applications and modern requirements. So this is a presentation about VME for military solutions. So I should say that all three of these boards are available in air-cooled variants, right up to we support -40 to +85 degrees C air-cooled boards. But we also have conduction-cooled versions of all three of these products. So some military applications require high levels of ruggedization and conduction cooling. That's an area where we have a lot of expertise, and we're very committed to maintaining that type of product in the future. So that's the advert over. So let's talk a little bit about what we're doing. And before the webinar, I tried to sort of think about, well, what are the sort of needs that we hear from some of our VMEbus customers, and how are we applying those to our products? And not surprisingly, Rob already talked about very long life cycles, backwards compatibility, but one of the areas where we've seen a lot of change over the last few years has been on the emphasis on security, not surprisingly. And unfortunately, some of those things, when we look at Intel processor boards, are difficult to make one solution that has fantastic backwards compatibility. So, for example, can run legacy operating systems, but can also provide all the necessary security capability that some of our customers are demanding in that space. So as well as being different performance levels, the three VME processor boards that we have in the market today have a different mix of capabilities that we're going to talk about in a little bit more detail now. So first of all, I want to talk about firmware integrity. So obviously, as we build these products and we ship them to our factory, we load firmware onto the boards. And all that firmware is really the basic root of trust of everything else that builds further on in the product. So we need to be absolutely sure that both that firmware is the right firmware when it was shipped from us, but also at all times within the life cycle of that product. The way we do that is by using a technique that Intel has codenamed boot guard, but the idea is really that there's a one-time programmable fused device. It's one of the major devices on the board. We actually load that device before it leaves our factory with a public key. We sign the firmware with the mating private key. When you power on the board, if the signature of the firmware doesn't match that that's fused into the board, then the board refuses to boot. And so that stops any of these man-in-the-middle attacks, and it stops any tampering with that firmware at any point during the life cycle of the product. So 2 out of the 3 boards that we have today have that feature enabled by default. And the other really good feature is that even though it stops unauthorized firmware, if we need to update the firmware at any time, that's obviously possible. We just make sure we sign it with the same key before it leaves our factory. So the firmware itself, and again, this is a very Intel specific thing, is there are various classes of firmware, which in the sort of strict definition are known as UEFI class 0, 1, 2, and 3. So this dates back to the early days of Intel processor boards when they were fitted with what was known as a BIOS. That's now colloquially called legacy BIOS. And over the last 10 years, we've been gradually migrating up the classes so that now we have 2 boards, or 2 out of the 3 boards, support what's called UEFI class 2. And effectively what that really means is they both support the legacy BIOS features and they also support the UEFI features. So the good thing about legacy BIOS is it gives you the ability to boot older operating systems. So maybe you want to load VxWorks 5, VxWorks 6, or maybe Windows 7, which require a legacy BIOS. The bad thing is that those are less secure. So if you want to load a modern operating system, so a version of Linux, Windows 10, VxWorks 7, or any of the other modern operating systems, then they only boot on an Intel processor if you have a full UEFI Class 3 BIOS. So there's a trade-off there between better security or backwards compatibility. As I say, 2 out of the 3 boards support both, but the third and newest board only supports UEFI boot. Now, just to fill in one more detail here is we have one other option other than a BIOS. That's that we can replace the firmware with a slimmed down version, a more lightweight version of that firmware, which boots a lot quicker. And that's really important for some of our customers who need really high or really quick startup times. And again, that is UEFI capable. The next thing I want to talk about is a Trusted Platform Module, or TPM, which is a little tamper-proof or tamper-resistant integrated circuit. And you can think of this as sort of, its main functionality is to act a bit like a safe. So it stores things like critical crypto keys that are needed to provide some of that root of trust that we talked about a minute ago. It can do other things like generate random numbers, but it's a very useful device and a mandatory device if you want to meet some of the latest standards. I've got one example of how the TPM can be used, and that's that you can actually record hashes of the various levels of firmware as you go through the boot process, starting with the BIOS, the bootloader, the kernel, the OS. You can actually store those in the TPM securely, and then you can actually use that later on as a measurement to be. You can go back and you can actually guarantee that you are running the correct firmware by validating those measurements. That process called attestation. The other thing I want to mention is that whilst all of our processor boards have a TPM fitted as standard, that TPM is now a TPM 2.0 and has been for a few years, which is the latest, or the current generation of TPM. There's a lot of chatter about this with Microsoft Windows 11, which is potentially mandating a TPM 2.2 to TPM 2.0. So moving on from the TPM and talking about that root of trust, the next level upwards is when you start to boot things like operating systems. And there is an easy way of doing that by using what's called secure boot. So this is a feature that you get as a virtue of using that UEFI firmware. And effectively what happens is that your operating system is validated, again, by the bootloader bit of the operating system is validated with a key that is stored on the product. So as we ship our boards, we ship them with the de facto Microsoft key, which is also used to validate Linux. But if you want to develop your own operating system or you're using a different operating system, we provide a means of updating those keys. So effectively, as a customer, you are able to provide your own key that will enable this to be validated, which it gives you that level of capability there. The next thing I want to talk about is storage. So many of our processor boards have a variety of different mass storage or storage capability. And storages are often, the onboard storage is typically used to boot the board unless you've got a network boot capability. But because the capacity of these storage devices has gone up quite dramatically, they're very often also used to store application data. And over the last 5 years, we've significantly changed our strategy to enable a much better level of security on those storage devices. So rather than using more commercially orientated devices like CFast and 2.5-inch drives, we've migrated to using predominantly now M.2 modules, but also almost every single one of our processor boards also supports a proprietary module, this AD230 device, which you see on the top right corner, which is about the size of a postage stamp, sorry. And there's a couple of key features that we're really worked very hard to deliver to our customers. The first of those is making sure that these are write protectable, because we have many customers who want to store their application or data on the device, and then they want to write protect it to make sure it can't be overwritten. The second feature is the ability to provide data rest protection. We do that with Opal encryption. So what that does is, as the data is stored on the device, it's encrypted. And so if you take that device out and plug it into another suitable board, you can't read the data off that device unless you can unlock it. Now, in a commercial environment, you usually unlock it by typing in a password. That's obviously not suitable for embedded use. So this is another area where we use that TPM, the Trusted Platform Module, store a crypto key in the TPM, and you can then unlock the storage module based on that key. So effectively what that does is it makes sure that the only board that you can read that storage device on is the one that it was fitted when you created that key. There's a couple of other things that we do as well, which again are very relevant to many of our VME and military customers. So we provide Builtin Test and not just the sort of firmware version of Builtin Test, but also operating system level Builtin Test. And we also have a further package that we offer, which provides a holistic approach to security to prevent unauthorized insertion or extraction of any of the firmware or data, in addition to the features that we talked about today. So that's quite a bespoke package. We have tailored that to many customers' needs, and we support these features across the board on the VME boards that we're showing here, and also all the other products that we do in our portfolio. So summing up, we've been around as a company 35 years. VME Bus has been going a little bit longer than we have, and it's definitely still going strong for us. I had a gentleman who I know contacted me before this webinar, sort of suggesting that VME was very much dead, but that, in our experience, is not the case. And we have worked very, very hard to keep our VME Bus products relevant. And I should say that we're still offering a roadmap of VME products. If you're interested in any future offerings, please contact us for more details. And with that, I'll hand back to you, please, John.
You're right, Nigel. It's not dead. It's 40 years old. It's only middle-aged. So on that note, just a quick reminder to send your questions in, your comments, or if you disagree with Nigel, we'd like to hear from you too in the question box. So, and I'd like to turn it over now to our next speaker, Ken Grobe. And once Ken is done, we'll start our Q&A session. Ken, take it away.
Thanks, John. Here we go. So, good morning. My name's Ken Grobe. I'm with Elm Electronic Inc. And today I'd like to talk about VME Bus military systems and follow up with what Rob and Nigel have discussed about VME Bus. Elm is a company that makes packaging for the VME Bus applications. We provide chassis, backplanes, and also equipment racks. I'd like to touch on how some of those are used in VME Bus applications. As Rob said, VME's been around for quite some time. And it served multiple market verticals: military and aerospace, medical, industrial, communications, transportation, and scientific. Applications like shipboard controls and comm, machine control, semiconductor equipment, railway switches, and things like particle accelerators and physics experiments in the scientific community. VME Bus is an open standard, as Rob mentioned, and it is managed by VITA, and it is contributed to through technical working groups by folks that build products with it and use it. When it was created, it addressed features that fit sort of the marketplace that it addresses. Modularity, in that the boards are like building blocks. It can be plugged in and removed from the backplane and upgraded, which provides feature sets for maintenance and or the ability to maintain and to change and support the chassis and the systems that use it. It, in addition to being pluggable, is backwards compatible, as Rob and Nigel mentioned. So it provides compatibility between newer versions of cards built to the later versions of the standard and older versions of the boards and backplanes that were made with earlier versions of the standard. The big thing with VME is that it provides a lot of user I/O to get signals in and out of the chassis. So systems can process information and exchange I/O in different forms to get the data in and out of the system. It's provided standards for ruggedization, and this card is shown as a conduction cooled module, and it's robust in that it provides robust in the sense of an ecosystem that provides software solutions for the hardware that's been created as plug-in pluggable modules, and it also supports long life cycles. The ecosystem is pretty big. Smart Embedded and Concurrent Computer being two people that make things, or two organizations that make things for VME Bus. Over the years, the ecosystem grew because of the standard and sort of nurtured an industry. So we have companies out there that supply multiple types of boards, including single board computers, I/O solutions, network switches, power supplies that plug in, backplanes and packaging, and all sorts of software solutions, including OSs to support the hardware. As far as performance, this is a slide out of one of the working groups that compared the different bus structures across parallel buses and then ultimately switch serial implementations of the VME bus hierarchy called VXS. You'll notice that in the middle, the practical bandwidth for VME64 was about 40 megabytes per second with a theoretical number of 80. This bandwidth figure has been quoted at 40, 80, 160, and then up to 320 as the transfer mechanism has evolved over time that the bus supports with VME64, VME64X, and then 2 ESST. This was a release 1.5 of the specification that implemented 320 megabyte per second transfer capability. Ultimately, in the mid-2000s, VXS was introduced around 2007 and 8, that introduced switch serial fabric and increased the bandwidth per link in the fabric section of the implementation at 2.5 gigabits by one link, which there were 8 links per node board in VXS, and then 2 switches that implemented the dual star network. So this allowed the bandwidth to increase from 40 up to multiple gigabytes per second, like in the 30s, of performance across the single VME bus chassis. Bookending it, looking at VME Bus from the beginning to the sort of this place that it is now, there was transition from parallel to serial. And this has taken place and is now used, the serial methods and the serial connectors are used in VPX, VITA46, and OpenVPX, VITA65 as migration paths for people to transition from 6160 cards that support VME up to higher performance technologies that leverage a lot of the base definitions that occurred earlier in the development of VME. The slide on the left indicates that you can have parallel legacy VME solutions in the same backplane as you can have the switch serial solution. And in actuality, the switch serial capability is combined with the parallel capability in a 6160 plugin that gives you 2 ESST parallel capability, so all the definitions that preceded it, along with the overlay of a fabric architecture that provides very high bandwidth. So this is pretty interesting because it provides backwards capability and preserves an investment, and then provides you a future solution based on fabric architecture. The slide on the right shows that capability across the transitions of the VME Bus spec as it was upgraded, and then the jump to VXS, which provides serial technology on top of the or alongside of the parallel technology, which gives you performance up into the multi-gigabytes per second in a VME Bus architecture. And this is, I guess, to look at that James Brown article that Rob referenced, the reason why you didn't see VME die an early death. So some of the elements defined by VME included the architecture, 8-bit through 64-bit data, and 16 through 64-bit address. And mostly it was used as, say, an A32, like D32 bus, or A32, and then 816 or 32-bit data transfers. But there was modes defined for 64-bit transfers to increase the performance. It defined the form factors 3U, 6U, and 9U, and these were defined against IEEE standards, so 11.0.1.x, sort of a suite of standards that define the sub-rack and the transition modules, and also define the backplanes. The backplanes originally started out with 3-row 96-pin connectors and then moved up to 5-row connectors for P1, which is the plug-in card connector, and J1, J2 for the backplane. And the backplane also provided a connector as time moved on with the 64X release that was called P0, gave you 95 extra pins. So both the cooling methods were defined, convection and conduction, defined by 11.01.1 and 11.1.2. And an interesting standard for mezzanines was developed called 1386, the common mezzanine standard, that allowed I/O to be implemented on mezzanines. So if you take a look at the improvements of and that are related to the major release of VME 64X, sort of midlife, it increased the power, the performance, and the I/O. And this is where the 160-pin connector was introduced, and adding P0 and 3.3 volts, 25 grounds, and improvements to EMI and ESD and better mechanical definition. And this table defines the pinout of the 64X implementation. So as you looked at VME advancing and consider its I/O capabilities, it's really essential to building a military system. VME expanded the I/O from using 96-pin connectors that allowed 64 bits of I/O, or 64 signals, rather, on the A and C rows of the connectors, and then increased it by 46 pins, implementing Z and D rows. So it expanded the I/O up over 100 pins. And then it also implemented this P0 connector, which allowed 95 extra pins of I/O. This allowed PMCs to be mapped using a standard called VITA35, which maps the I/O from the PMCs to the P2 connector and the P0 connector, letting you support up to 64 bits on the P2, and actually more than 64 bits on the P2, and 64-bit or signals rather on the P0. Other things that were updated included the introduction of the XMC standard, which is VITA42, which supported a higher transfer rate connector, and then ultimately a VXS supported PCIe interconnect, serial rapid I/O interconnect, and gigabit interconnect through the fabric connectors, which you can see in the backplane on the sort of the middle of the slide. So here you can see that VME Bus supported both the parallel I/O and the fabric connections, and you could have backplanes that had just the parallel connections and and slots that had the fabric connections in them, so you could try to sort of mix both capabilities, legacy and serial capability in the same backplane. So with all these capabilities, VME lets you build building blocks, and the building blocks can be constructed out of the I/O schemes that existed for mezzanines, and then the base cards, either the single board computers like Nigel was talking about with the different VME Bus SBCs that support PMC and XMC I/O. By doing this, you can increase the functionality of the single board computer or a carrier, which just has slots for the PMCs or XMCs. When you add software like VxWorks, you end up with a subsystem on a slot, and this lends itself to what Rob was talking about as compression of the functionality. Well, now you get a very dense solution in a 1/8 inch wide card that can be replicated multiple times in the backplane. We called this solution an ApplePack and offered it around concurrent cards and also Motorola cards and other cards made by other manufacturers. So this was sort of like a turnkey board that had specific I/O functionality, and in this case also storage functionality. So some examples of these in different applications. We had VME 64X implementations of processors and I/O carriers that allowed you to have gigabit Ethernet and storage, and also solutions that had PowerPC capability, legacy stereo I/O, VxWorks capability, and removable storage. These are sort of bricks that were defined with mezzanines and processors to achieve a certain level of functionality. These were plugged into chassis that provide VME 64X backplane connectivity, and in this case also isolation in this rugged chassis called a 12R2. So if you looked at this from the top level, as integrators demanded function using VME technology, they had to package it in different ways to achieve ruggedization. They also needed to interconnect it and support things like networks. And this is an example of a rugged VME 64X 24-port gigabit switch that could plug into a VME Bus backplane and provide 24 Ethernet ports that were switched via switch fabric inside the card to allow you to connect multiple Ethernet devices. Then next we see a chassis that implements a full system that used 2 PowerPCs and a 3D model here of the chassis itself that uses horizontal mount 6160 VME cards connected together on the backplane, and then rugged connectors on the back with 38999 that implemented VxWorks. In this case, there were 2 boards, so it was multi-processor, and they were connected together through the Ethernet switch and then also connected to the outside world through the Ethernet so that you could put this up on a network and communicate to the chassis. As you move up the food chain, it's necessary to take chassis and put them in rugged racks that would survive the shock and vibration levels required by the end system implementation. In this particular application, used Intel SBC, mezzanine I/O, a network switch, rugged displays, VxWorks, system monitoring to monitor the health, and actually use multiple chassis per rack. When you do that, then you need to get the I/O in and out, bring it off the back or the top of the chassis, and bring it out through connectors like 38999 connectors on the back on the rear panel to get the I/O to the outside world. Standards like MIL Standard 461, MIL S901D, and 167 provide the standards for military systems relative to EMI, shock, and vibration. And these components, these racks, needed to be able to survive that. And in essence, the boards inside the chassis, inside the racks, needed to be able to survive those levels of vibration and shock, which is part of the integration effort required when you use VME Bus cards in a system. You need cards that are ruggedized to be able to be combined and integrated and be delivered in a solution that'll perform at those levels. The bottom picture shows a display-oriented rack that allowed rugged displays to be mounted along with VME Bus hardware in a rack-level implementation. So bringing it to an end here, as systems were built, they needed to be thermally modeled, and the backplanes needed to be simulated. So certain tools were needed in the design to close the loop. 3D modeling programs to design and develop the chassis, which are often tailored in most of the VME Bus systems that were out there, and then ultimately deployed. So these are some of the tools that we use to do that. And then finishing up, some use of chassis, racks rather, that were rugged, that allowed ruggedized chassis with 64X backplanes to be mounted and then shock isolated with rope isolators. And these are made out of aluminum, bolted together so that they can be put together and taken apart, and very, very actually strong and robust enclosures. And to the right, you see similar rack level solutions like that house displays and allowed VME Bus technology to be used in the bays that were below it. So lastly, to close the loop around the enclosures, these standards imply that tests need to be run, and these are some of the fitments to show vibration testing of racks and light hammer testing of complete enclosures of the electronics to test them at the shock levels that would potentially be encountered on the platforms that they're mounted on. So in summary, VME's been a workhorse technology for military system integrators, and it's still going. There's still new design-ins occurring. With VME Bus, we're still shipping quite a bit of the packaging and system technology associated with it from Elma. So it's still out there and being supported and available for system integrators to use today. So I'll turn it back over to John.
Thanks, Ken. Great presentation. Great all three gentlemen. And so let's start our Q&A. I got a question here for Rob. What factors are typically the most critical when trying to decide on an upgrade path for a VME processor card?
Yeah. In many cases, it is really the software you're using, and do you have the ability to migrate or not? That seems to be usually that's usually the first question I ask somebody. What are you using today? What do you want to use? Because that really does drive a lot of decision making. We have processor boards that support older versions. It's usually like 551 on VxWorks, and then our newer stuff doesn't go down that low. So that's usually the starting point, and then backplanes are probably a near second.
Next question from the audience. As we accept and adopt AI and machine learning technologies, what are the implications for VME supporting these system capabilities? Who would like to take that? That's for anybody who wants to take a stab.
Yeah, Nigel, I'll take that. So if you want to add AI capability to an existing VME platform, that is possible. It would be a relatively lightweight inferencing application. 2 of our 3 VME processor cards today support that type of capability. However, I'd strongly recommend that if you want to start an AI or neural network, deep learning application, it'd be much better starting that out with something like VPX technology, because it allows much higher bandwidth connections. You can get a lot more flexibility with multiple CPUs or CPU GPUs and CPU FPGAs for acceleration of the AI algorithm.
Anybody else want to comment on that? That's an open question.
Yeah, I think Nigel hit it. It's if you're trying to find a way to integrate it into an existing VME Bus application, it is going to be limited. So you need those high-speed serial interfaces to move data around effectively, especially if the modeling that you're doing is really utilizing both a GPU and a processor. In some cases, each one has its special sauce for being able to do that. So I agree with what Nigel said.
Okay. Next question. I'm going to throw this one to Ken. VME, like 1553, has lasted decades with orders still coming in. Much of the longevity, as you guys have talked about, is due to the long life of military programs. And how VME led to VXS to VPX, which is now contributing to the SOSA standard. So, do you see similar longevity with the SOSA standard as it takes advantage of these other open standards we've talked about? Will 40 years from now, will we be wishing SOSA happy 40th? Will VME just be the grandpa in the room too? Still.
I think so if you look at this as a progression, where SOSA uses a hardware layer that's based on OpenVPX, and OpenVPX is, let's say, maybe a little over a decade, between VPX and OpenVPX, a decade old. I think you continue to see those standards maintained like you saw VME. It's kind of amazing that VME's been supported as much and as long and as strongly as it has to keep it maintained and to keep it growing. And I think with the VME Bus or VITA Trade Association and all the members who support both VPX and OpenVPX, and then the community that supports SOSA, I think you'll continue to see that last for a really long time too.
Okay. Question from the audience. This is an interesting question. I kind of thought of it myself earlier. It was talked about how VME is still in high demand. For new initiatives and program starts, what percentage does anybody have any idea, are using VME-based subsystems? And what is the prominent bus architecture that's being selected for new program starts? I would think it's VPX, but is there new wins getting VME? Anybody want to?
I can comment on it just from our perspective. I mean, if you look at what we ship a lot of VME, but the VME's been designed in typically for a long time. However, there are new starts for VME for various types of platforms at the chassis and at the rack level that we're seeing. So we're still seeing, even with the maturity of VME, folks starting new designs, and in some cases, the new designs are tech refreshes of existing platforms. So there's like a trade-off that you have to decide: are you ready? Is the program manager ready to, or the owner of the system ready to make the conversion all the way up to a new architecture? So for new starts, we do see most of the new starts going towards things like VPX and OpenVPX.
We've seen situations where we've had. Yeah, I was just going to say that we've seen situations where a customer that might have some custom boards they've designed might start a new project in VME because they already have a history with the existing I/O that they want to do. But it kind of fits into that legacy theme anyway. I mean, it's most of the people we deal with are legacy. Nigel might have, they might see some new guys because of the newer style processors.
This question is going to go ahead. Sorry.
Carry on, John.
Yeah. This one's from me. I mean, in the article Rob referenced that he wrote for us, he talked about at the Embedded Tech Trends conference, or the precursor to that bus and board. There were a lot of talks about the market presentations and where VME is versus VPX, and we're starting to see VPX, kind of surpass VME in orders. But one of the things that always happened over those market presentations is they mostly focused on companies like yourselves and what you supply to the marketplace. But they didn't really always cover, when the prime contractors would roll their own VME designs, making it harder to track market size. So does it still occur with VME? Are they still rolling their own, or is it more that's because it's an older technology, they're kind of outsourcing it? The prime contractor perspective, that part of the market.
I think they're not doing new. I think they're just maybe still manufacturing some existing modules that they use for some key programs.
But the majority of the market these days is really the OEM when it comes to VME. It's you guys.
I would think so. I don't know if I have definitive proof of that. That's what I would think.
There may be.
Go ahead.
There could be proprietary cards or certain cards that were developed by the prime that they'll continue to build. I think we see that. So there might be a part of the infrastructure that needed either the VME bus chassis backplane, maybe some of the cabling, and some of the boards, depending on what the purpose of the system really was. For instance, you might have some specialty FPGA-based board or other I/O board or other processing functions that were developed by the next higher level integrator.
I agree, Ken. I think that those secret source type components are still very much proprietary, whereas the relatively easy processor boards and the I/O boards and the chassis and things which are perhaps more commercial orientated, they're now mainly outsourced.
Thank you, gentlemen. And that's kind of bringing us to the end, but I have a comment, not a question that was submitted, that I have a gentleman who says he was the first in Europe to introduce VME back in 1981, and he still has a copy of the magazines. Well, I'm glad to see that, and you're still reading. But that he says there's always going to be more to say about VME. So, and I would agree, so keep doing what you're doing. And just a side note, we produced the first VME Bus magazine. I think it'll be 40 years next year. So, and that magazine is still going strong, called Builtin Technologies today. So I want to thank everybody for attending today's webcast. This is our time limit for today, as I mentioned. We didn't get to all of your questions, but someone will get back to you after the webcast for more information. Thank you, Rob, Nigel, and Ken for speaking today, and Concurrent Technologies, Elma Electronic, and Smart Embedded Computing for sponsoring the event. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will be archived online today and be available for 1 year. There will also be an MP3 version of the event available. Thank you all for attending. I look forward to seeing you on future Open Systems Media webcasts. Goodbye.